we now learn about continuous random variables and probability density functions. Continuous random variables are typically referred to with capital letters, like capital X, capital Y, or capital Z, or any other capital letter. And we use continuous random variables to model continuous phenomena or quantities, things like length or time or even weight or mass. And as the name suggests, the value that a continuous random variable, capital X, could take depends on chance, in other words, probability. And a typical type of question that we'll seek to answer could be something like, what's the probability that a person taken at random measures less than 1.75 meters? And in that example, the continuous random variable would be the height of the randomly selected person. To answer that type of question, we're going to need two functions. And the first of those two functions is the probability density function. Now, the probability density function is frequently referred to as P, D, F, and put simply, it's a function like many other functions that we've seen before, and we usually call it f of x. And this function has a couple of properties that must always be true and always be kept in mind. The first is that f of x will always be greater than or equal to 0, and that's for all real numbers. The second important property is that if we integrate this function over all real numbers, then it will always equal to 1. What that tells us is that the area enclosed by a probability density function and the horizontal axis will always be equal to 1. The second function that we need to calculate probabilities is known as the cumulative density function. And the cumulative density function is sometimes called the distribution function or the cumulative distribution function, and we'll usually refer to it as CDF. Now, the CDF, or cumulative density function, is the function with which we actually calculate probabilities. And it's defined as capital F of x, and it's equal to the integral from -infinity up to x of the probability density function. So I'll write f of t. Now, don't let the fact that I'm writing t here instead of x bother you. We simply do that to distinguish the variable from the upper limit of the integral. And we calculate probabilities with the cumulative density function using the fact that the probability that the continuous random variable capital X be less than or equal to x is equal to the cumulative density function. And combining these two things, we'll often simply write that the probability that the continuous random variable be less than or equal to x is equal to the integral from -infinity to x of the probability density function. So, looking at these two functions we've just defined here, what's important to realize is that the function used to calculate probabilities is the cumulative density function. The probability density function, that's lowercase f of x, serves to define the contour or the envelope of the distribution. In other words, it's what gives us the equation of the curve here. And so given a probability density function, which I'll make a quick sketch of here, the probability that the continuous random variable be less than or equal to some value k is equal to the area enclosed by the curve of the probability density function and the horizontal axis up to k. And we're going to see an example of how to do that in just a minute. Before doing so, though, let me highlight something very important. Let's say we wanted to calculate the probability that a continuous random variable equal to some specific value k. Well, when working with continuous random variables, this will always equal to 0. And when we first see that result, it can be slightly confusing. But here's why this result is always true. It's important to realize and keep in mind that a continuous random variable can take on an infinite number of values. And so to make the link with probabilities, what they're saying there is that there is an infinite number of possible outcomes. Consequently, the probability that the continuous random variable take on any specific value will tend towards 0. So much so that we state that it's equal to 0. Okay, now let's go ahead and look at a quick example with an actual probability density function and how that's integrated to define the cumulative density function to calculate the probability that the continuous random variable be less than or equal to some value. I'll start by making a bit of space. There we go. As an example, let's say we're dealing with a continuous random variable, which we'll call capital X, which has a probability density function defined as f of x equals to the piecewise function, which is cosine of x over 2, for all x between negative pi over 2 and pi over 2, and it's equal to 0 elsewhere. In other words, this function would look something like this, where it touches the x-axis at negative pi over 2 and pi over 2, and it reaches a maximum height here, where it cuts the y-axis, of 1 over 2. And looking at this quick sketch here, we can see that this confirms one of the properties we stated earlier on, that was the probability density function is always greater than or equal to 0. Indeed, the y values of this curve are all greater than or equal to 0. And you can go ahead and check, but if you were to calculate the area enclosed by this curve and the x-axis, you'll find that the area enclosed is equal to 1, which would confirm the second property we stated. Now, let's say we had to calculate the probability that this continuous random variable be less than or equal to pi over 6. Then, using the definition that we stated earlier on, that I'm currently pointing towards in red here, we can state that this probability is equal to the definite integral from negative infinity up to pi over 6 of the probability density function, that's f of x. And now looking at the probability density function, we can see that it's equal to cosine of x over 2 for x between negative pi over 2 and pi over 2, and it's 0 everywhere else. Consequently, the lower limit of this integral will change, and we can write this integral as follows. We can state that this equals to the definite integral from negative pi over 2 up to pi over 6 of cosine of x over 2. And this definitely makes life easier. We no longer have negative infinity as a lower limit on our integral. We have negative pi over 2. And remember, the reason behind this is that f of x equals to 0 for all real numbers between negative infinity up to negative pi over 2. Now we can write this integral as 1/2 times the definite integral from negative pi over 2 up to pi over 6 of cosine of x. And I'll just carry on with the working on the right-hand side here. That's equal to 1/2 times, in square brackets, the antiderivative of cosine of x, which is sine of x, with lower limit negative pi over 2 and upper limit pi over 6. So that's equal to 1/2 times sine of pi over 6 minus sine of negative pi over 2. And sine of pi over 6 equals to 1/2, and sine of negative pi over 2 is equal to negative 1. So we have 1/2 times 1/2 minus negative 1. That's equal to 1/2 times, in square brackets, 1/2 plus 1. That's equal to 1/2 times 3 over 2. And 1/2 times 3 over 2 is equal to 3/4. Finally, we can state that the probability that the continuous random variable be less than or equal to pi over 6 is equal to 3 over 4, which is 0.75. And that's the probability we were after. Looking back at the quick sketch we made at the beginning, this probability corresponds to the area enclosed by this curve and the x-axis between x equals to negative pi over 2 and x equals to pi over 6. And that's the area I'm hatching right now in green. And so that's one of the typical types of probabilities that we'll be calculating when working with continuous random variables. The other type of probability that we'll be calculating will look something like this. The probability that the continuous random variable, capital X, lie between A and B. And in fact, let's go ahead and use this probability density function again to see a quick example of that. Let me just make a little bit of space again. There we go. So again, let's say we're given the probability density function defined as f of x, which equals to the piecewise function defined as cosine of x over 2. That's for x between negative pi over 2 and pi over 2. And it's equal to 0 elsewhere. And now say we were asked to find the probability that the continuous random variable capital X lie between 0 and pi over 6. Well, to find probabilities like these, we can use the following rule. The probability that a continuous random variable lie between two values, say a and b, equals to the definite integral from a to b of the probability density function. Consequently, we can state that the probability that the continuous random variable lie between 0 and pi over 6 is equal to the definite integral from 0 to pi over 6 of the probability density function. And now 0 and pi over 6 are both within the interval negative pi over 2 to pi over 2, so the probability density function equals to cosine of x over 2. So this integral becomes the definite integral from 0 to pi over 6 of cosine of x over 2. And that's equal to 1/2 times the definite integral from 0 to pi over 6 of cosine of x. Integrating, we find this equals to 1/2 times, in square brackets, sine of x, with lower limit 0 and upper limit pi over 6, and that's equal to 1/2 times sine of pi over 6 minus sine of 0. And I'll carry on with the calculation to the right-hand side here. We have sine of pi over 6, which equals to 1/2, and sine of 0, which equals to 0. So this becomes 1/2 times 1/2 minus 0, which equals to 1/2 times 1/2. Finally, we can state that the probability that the continuous random variable lie between 0 and pi over 6 is equal to 1/4, which is 0.25. And that's the answer. If we were to illustrate this with the curve of the probability density function, what we're looking at here is the following. We have our xy grid, a portion of the cosine curve from negative pi over 2 up to pi over 2, with a maximum height of 1 over 2, and the probability we have just calculated corresponds to the area enclosed by this curve and the x-axis between x equals to 0 and x equals to pi over 6. So that would be this area that I'm currently hatching in green. And there we go. So we've now seen the two types of probability calculations that we'll be doing with continuous random variables. Now I'll finish this tutorial by highlighting one last important point. When working with continuous random variables, we need to keep in mind the following result. The probability that the continuous random variable be less than or equal to some value k equals to the probability that that same continuous random variable be less than k, where k is some number. Now this is an important result in the sense that it's very different to what you may have come across when working with discrete random variables. So I'll say it again, there is no distinction to be made between these two probabilities. They are calculated in exactly the same way using the cumulative density function. A direct consequence of this is the fact that the probability that a continuous random variable lie between two values a and b can be written in either of the following ways. In other words, all four of these probabilities are equal and are calculated in the same way by integrating the probability density function between a and b. So for instance, looking back at this example we just worked through, we could have written probability that x be greater than 0 and less than pi over 6. And the calculation and the result would have been exactly the same. And there we have it. We've covered most of the key things that we need to know when learning about continuous random variables and probability density functions. And that's it for this tutorial. I really hope that helped, and if it did, please hit like on this video and even subscribe to our channel because that really does help us. I'll see you soon.